Welcome to the deep dive. Today we're jumping straight into, well, the engine room of the modern cloud. We're talking about containerization on AWS. It's the architecture powering, something over 60% of cloud deployments now. It's massive.
Oh, absolutely. It's pretty much the standard. And, for anyone building apps today, the thing they touch every single day is that container image. It's this neat little package, lightweight, standalone, immutable, bundles up all your code, dependencies, everything you need. It's really the tech that finally killed that age-old problem of, it works on my machine.
Right. And that immutability, that portability, it sounds fantastic for moving fast, for scaling up and down. But looking at how this all plays out, the connection between the AWS architectures, ECS, EKS, Fargate, and how people actually secure them, it seems incredibly complex, sometimes dangerously so.
And that complexity, that's exactly why we're doing this deep dive. Our mission today is really to give you a shortcut through that complexity. We need to understand why, even with AWS providing these incredibly robust tools, we still see figures like 70, even 80% of container security incidents coming down to, human error, simple configuration mistakes.
80%, that's huge.
It is. We have to unpack this paradox. AWS infrastructure, super secure. But containers, fundamentally, they still rely on that shared host kernel, unlike a traditional VM. And that sharing, it just magnifies the risk if you slip up on the config. So we're focusing today on what you, the customer, own, what you absolutely must get right in this environment.
Okay, so let's start peeling back those layers, the architecture. Because that first big decision you make, the orchestrator that really sets the stage for your security and, frankly, your operational headaches. We've got the two main players, Amazon ECS, Elastic Container Service, and Amazon EKS, Elastic Kubernetes Service.
Yeah, and they cater to pretty different needs, different philosophies almost. ECS, that's the AWS proprietary one. It's often seen as lighter weight, simpler perhaps. If you're deeply embedded in the AWS ecosystem already, ECS often feels like the path of least resistance. You're working with native concepts like task definitions, clusters, services. It's all very tightly woven into AWS.
I kind of think of ECS like getting a custom-tailored suit, right? Made specifically for the AWS environment.
That's a great way to put it. And a key technical point, ECS uses the OSVPC network mode. What that means is every single task, every running container group gets its own Elastic Network interface, an ENI.
Okay, its own network card, essentially.
Basically, yeah. And that makes network segmentation really clean using standard AWS tools. You can apply very specific security group rules directly to an individual task. So you get really granular isolation from other tasks running on the same host, just using the tools you already know in AWS.
Got it. So tight integration, potentially lower complexity, nice native network security. Then there's EKS, the industry standard, Kubernetes.
Right, EKS is Kubernetes as a service on AWS. It's the choice if you need portability, maybe you're running hybrid cloud, or you just want access to that huge open source Kubernetes ecosystem. The big value prop here is that AWS manages the Kubernetes control plane for you, the API server, et cetera, all that complexity. They guarantee its uptime across multiple AZs. And honestly, managing a Kubernetes control plane yourself, it's notoriously difficult to secure and operate, so AWS takes that heavy lift.
And the networking model there is different too, right? It's more the standard Kubernetes way.
Exactly. EKS uses the VPC CNI plugin. This means every pod, the Kubernetes equivalent of a task, gets its own IP address directly from your VPC's IP range.
Okay, so an IP per pod.
Correct. Now, the trade-off with EKS, even though it's managed, is often more complexity overall. There's just a steeper learning curve compared to ECS sometimes. But you get immense flexibility, especially for those really complex stateful applications or multi-tool environments, and that IP per pod model. It lets you use standard Kubernetes network policies for fine-grained segmentation, similar in effect to security groups in ECS, just implemented differently using the CNI.
All right, so ECS for AWS native simplicity, EKS for flexibility, and the K8 standard. But then there's this other piece that really changes the security game, Fargate. You called it security by abstraction earlier. It's not just about not managing servers, is it?
No, not at all. Fargate is fundamentally a different security posture. It acts as a serverless compute engine for both ECS and EKS. You tell it what container image to run, how much CPU and memory, and it runs it. The key is what it replaces. With ECS or EKS on EC2, you manage the underlying worker nodes, the EC2 instances, patching them, securing them, scaling them. Fargate eliminates all of that.
But the real magic, the security differentiation, is how it runs the containers, right? Something about micro VMs.
Precisely. This is the absolute crucial point for everyone listening. When you launch a task or a pod on Fargate, AWS provisions a dedicated Firecracker micro VM just for that workload. Firecracker is this lightweight virtualization tech AWS developed, built for speed and strong isolation. Each workload gets its own tiny VM with its own kernel.
Its own kernel, so no shared kernel like on EC2.
Exactly. That micro VM boundary is hardened. It fundamentally prevents one container workload from escaping and accessing the underlying host, or critically, accessing other workloads running on the same physical hardware.
Okay, wow. So that eliminates a whole class of attacks we hear about, container escapes, kernel exploits affecting neighbors.
It does. Things like trying to exploit a kernel vulnerability to get root on the host, or one container reading the memory of another. Fargate's isolation model basically makes those impossible between tasks or pods.
So if Fargate offers this incredible security benefit, why isn't everyone using it? Why stick with EC2 nodes and accept that shared kernel risk? What's the catch?
That's the million-dollar question, isn't it?
Yeah.
It comes down to control and specific use cases. Fargate is fantastic, especially for stateless web apps, APIs, batch jobs, where that strong isolation is perfect. But you give up low-level host access. Need to run a daemon set in Kubernetes to deploy a monitoring agent on every node. Can't do that on Fargate. Need privileged container access for certain tools. Nope. Need direct access to the host's network stack. Host network. Not possible.
Ah, okay. So if you have specific operational needs or legacy apps that require that deep access, Fargate might be too restrictive.
Correct. Fargate prioritizes security and simplicity through abstraction. If your workload demands fine-grained control over the host environment, you're pushed back towards managing EC2 worker nodes yourself, and you implicitly accept the security trade-offs that come with that shared environment.
Understood. Control versus managed isolation. That's a key architectural decision point. Let's quickly zoom in on the container image itself. We mentioned it's the core artifact. How does its construction impact security?
Immensely. It's the very first place security thinking needs to happen, the shift-left idea. Images are built in layers, right? You start with a base image like Alpine or Ubuntu, and each instruction in your Docker file adds a new layer on top.
And that layering is good for efficiency, sharing common parts.
Exactly. But your choice of that base image is critical from a security standpoint. Using a minimal base, like Alpine Linux, which can be under 5 megabytes, dramatically shrinks your attack surface. Why? Because it contains only the absolute essentials. Fewer libraries, fewer utilities, fewer things that could have known vulnerabilities, CVEs, or that an attacker could use if they got inside.
So choosing, say, a full Ubuntu base image just because it's familiar, you're potentially bringing in hundreds of extra packages and potential risks that your app doesn't even need.
Precisely that. You're basically carrying a bigger target onto the battlefield for no good reason. Reduce the footprint, reduce the risk. And the golden rule here, images must be immutable. Once you build it, that's it. You don't patch a running container. You don't SSH in to tweak things. You find a vulnerability. You rebuild the image from the source, scan it, and redeploy.
Got it. Scan early, scan often, keep it minimal, and treat it as disposable.
That's the philosophy. Security scanning has to be a mandatory gate in your CI/CD pipeline before that image ever gets pushed to a registry like ECR, let alone deployed.
Okay, this all flows naturally into the shared responsibility model. It's a concept AWS talks about a lot, but in the context of containers, it seems even more critical to get right. Where exactly does AWS's responsibility end and ours, the customers, begin?
Let's draw that line nice and clear. AWS is responsible for the security of the cloud. That means the physical data centers, the global network, the hardware, the hypervisor layer that separates VMs. And critically, in the container world, they're responsible for securing the control planes, the EKS API servers, the ECS schedulers. If you're using Fargate, they're also responsible for securing the Firecracker micro VM layer and the underlying host it runs on. They provide the secure foundation.
Okay, so the infrastructure, the managed services control planes, and then we, the customer, are responsible for security in the cloud.
Exactly. You own everything you put on that foundation. Your application code, obviously. The container images you build or pull, including all their dependencies. How you configure networking your VPCs, your subnets, your security groups, your network ACLs. How you manage identity, those crucial IAM roles and policies, and data encryption, both in transit and at rest. And here's that crucial distinction again based on architecture. If you choose to run on EC2 worker nodes, you also own patching and securing the operating system on those nodes. Choose Fargate. AWS takes that host OS burden off your plate.
It's really clear how much responsibility sits with the customer's configuration choices. Which brings us back to that alarming statistic. 70–80% of breaches are down to customer misconfiguration. It's not AWS failing, it's us messing up the settings.
It really is the dominant factor. The platform is strong, but common configuration mistakes leave the doors wide open. And honestly, we see the same patterns over and over again in security reports. There are maybe 4 main categories of pitfalls.
Okay, let's break those down. Let's pitfall number 1. I suspect it involves IAM.
You nailed it. Overly permissive IAM roles. It's absolutely the most common and damaging mistake. It's often just easier, right, to give a role administrator access or broad permissions like S3 instead of carefully crafting a least privilege policy. But think about the blast radius. An attacker compromises one container, maybe through a simple web vulnerability. If that container's role is overly permissive, they instantly have the keys to the kingdom. They can access sensitive S3 buckets. They can modify security settings. They can maybe even disable login like CloudTrail to cover their tracks.
So least privilege isn't just a nice to have, it's probably the single most important containment strategy.
It is the fundamental way you limit the damage from an initial breach. It's non-negotiable.
Okay, what's pitfall number 2?
Secrets management, or rather, lack thereof. Hard-coding sensitive stuff, API keys, database passwords, tokens directly into container images, environment variables, or configuration files.
Oh, yeah, I've seen that. Developers trying to move fast.
Yeah, exactly. But it's incredibly risky. If an attacker gets any kind of read access to the container's environment or its config files, those secrets are just sitting there in plain text. Services like AWS Secrets Manager or Parameter Store are designed specifically for this. They store secrets securely, encrypt them, manage rotation, and inject them into the container only when needed, often as mounted volumes. Using these tools is essential hygiene.
Makes sense. Avoid hard coding at all costs. Pitfall number 3.
Insecure network configurations. Just relying on the defaults, basically. This could mean leaving default security groups allowing all traffic, or maybe overly permissive network access control lists and ACLs between subnets. Even if containers themselves provide some isolation, if your network allows wide-open communication, an attacker who lands in one container can easily scan the internal network, find other vulnerable services, and move laterally. Defense in depth means assuming other layers might fail, so your network segmentation needs to be tight. Deny by default.
Right. Don't assume the container boundary is impenetrable. Network rules matter. And the final common pitfall.
Using unverified or outdated container images. Pulling base images from public repositories without scanning them, or just failing to update your own based images regularly. You could be deploying an image with hundreds of known CVEs baked right in. That's just inviting trouble. The time between a vulnerability disclosure and active exploitation is shrinking fast. Continuous scanning of your image registry, like ECR, is crucial to catch these things before they get deployed.
Okay, those 4 IAM, secrets, networking, image hygiene seem like the big ones. So how do we build a robust defense? It sounds like we need layers, that defense in-depth approach. You mentioned shift left and shift right.
Exactly. It's a two-pronged strategy. Shift left is all about prevention, building security into the development and deployment process before anything hits production. This means integrating security tools directly into your CI/CD pipeline. Mandatory vulnerability scanning for every image build using tools like Amazon Inspector or open source options like Trivy or Claire. It also means generating a software bill of materials, an SBOM.
An SBOM, why is that so important? Sounds like paperwork.
It might seem like it, but it's actually a powerful incident response tool. An SBOM is a detailed list of every single component, library, and dependency and their versions inside your container image. So when the next log4 shell type vulnerability hits a common library, you don't have to guess which applications are affected. You query your SBOM database and instantly know exactly which images and running containers use that vulnerable component. It allows for surgical patching instead of panic.
Okay. Visibility for rapid response. Makes sense. What else is part of shift left?
Basic hygiene, like making sure containers run as non-root users whenever possible. This drastically limits what an attacker can do even if they do manage to exploit a vulnerability inside the container. Don't give them root privileges if they don't absolutely need them.
All right, so shift left is prevention in the pipeline. What about shift right? That's detecting things that slip through.
Precisely. Shift right is about runtime detection and response. Because, let's be honest, zero-day vulnerabilities happen, and misconfigurations can sometimes drift into production despite our best efforts. So you need to monitor what's actually happening in your running environment. Tools like Amazon GuardDuty play a big role here. It analyzes AWS logs, CloudTrail API calls, VPC network flow logs, DNS queries looking for anomalous or malicious activity patterns. like a container suddenly trying to communicate with a known crypto mining pool, for instance.
Okay, so analyzing the environment's behavior.
Yes, but increasingly, effective shift right also involves looking inside the running containers and at the host level, especially if you're on EC2. This is where kernel-level monitoring comes in, watching for suspicious system calls, unexpected file access, or network connections that deviate from the baseline.
Okay, let's pivot now from the configuration side to the actual vulnerabilities themselves, especially those that exploit that shared kernel model we talked about on EC2. What are the really high-impact threats we need to understand?
Well, the fundamental risk on EC2 stems directly from that shared Linux kernel. If there's a vulnerability in the kernel itself, and there have been famous ones like dirty CIW or various exploits related to melee groups, a compromised container can potentially leverage that flaw. The goal is usually privilege escalation, breaking out of the container's limited view, and gaining root access on the host EC2 instance. Once an attacker owns the host, they effectively own all the other containers running on it.
Right, the noisy neighbor problem becomes a catastrophic security failure. We saw a really significant example of this recently, didn't we? The leaky vessels vulnerability.
Yes, that was a big one. Specifically CVE 2024-2626, which was a flaw in Runk. Now, Runk is the low-level container runtime, the piece of software that actually creates and runs the container process. This particular flaw allowed an attacker inside a container, through a cleverly crafted file system mount operation, to essentially break out of the container's isolation and gain root access on the underlying host machine.
Escape the container, own the host. And the scary part was how widespread it was.
It's extremely widespread. Initial scans suggested something like 80% of container environments globally were vulnerable when it's disclosed. That's a shocking number. It points to a systemic issue with keeping the underlying host OS and runtime components patched and up to date across the board.
80%, wow. So the mitigation is patched frantically, or?
Or choose an architecture that sidesteps the problem.
Hmm?
Again, this highlights the Fargate advantage. If you had exploited that Runk flaw inside a Fargate task, you'd escape the container. But you'd land inside the dedicated Firecracker micro VM. That micro VM has no access to the underlying physical host or other tenants' micro VMs. It would simply be terminated and replaced. The exploit chain is broken right there. On EC2, you need constant patching, plus potentially using additional hardening tools like Aparmer or Solidus profiles to further confine containers.
It really underscores how architecture is security. Now, attackers rarely rely on just one trick, right? They chain vulnerabilities together. Can you walk us through a typical attack progression after they get that initial foothold in a container?
Absolutely. The initial compromise might be relatively minor, maybe a server-side request forgery, SSRF flaw in the web app, or perhaps hitting an accidentally exposed API endpoint that gets them inside. From there, the immediate goal is usually reconnaissance and privilege escalation. They want to find credentials or ways to move laterally. And the number one target for credential theft inside AWS is often the Instance Metadata Service, IMDS.
Ah, the magic IP address, 169.254.169.254. Why is that specific local address such a goldmine for attackers?
Because the IMDS provides information to the EC2 instance about itself. Crucially, this includes temporary security credentials associated with the IAM role attached to that EC2 instance, the instance profile. If a container running on that instance has network access, which most web applications do, an attacker inside the container can simply make an HTTP request to that local IP address and retrieve those temporary AWS credentials.
And if the EC2 instance itself has broad permissions attached to its role?
Then the attacker inherits those permissions. If the instance role can, say, read from many S3 buckets or describe other EC2 instances, the attacker now has those powers. Without needing a container escape or a kernel exploit, they just stole the host's identity credentials. It's a classic privilege escalation path.
That seems like a massive hole. How does AWS recommend mitigating that specific IMDS credential theft vector, especially in Kubernetes on EKS?
The primary mitigation, and it's a really important one, is called IRSA IAM roles for service accounts. Instead of letting pods inherit the potentially broad permissions of the underlying EC2 nodes role, IRSA allows you to associate fine-grained IAM roles directly with a specific Kubernetes service account. When a pod configured with IRSA starts up, it gets a special Kubernetes token. It uses this token to request temporary AWS credentials from a secure AWS endpoint. The key is that these credentials are specifically scoped to the permissions defined in the IAM role associated with that pod service account, not the host's role.
So it binds the AWS credentials tightly to the specific workload identity, not the general host identity.
Exactly. It uses token binding and audience validation. It drastically reduces the value of stealing the underlying EC2 instance credentials via IMDS because those credentials likely won't grant access to the sensitive resources the attacker really wants. IRSA significantly limits the blast radius of a container compromise if configured correctly with least privilege roles.
That's a much better model. Okay, one more area we have to touch on regarding vulnerabilities, the supply chain. Log4Shell was the wake-up call for many.
Oh, Log4Shell, CVE 2021-44228, was absolutely a defining moment. A single vulnerability in a ubiquitous Java logging library, Log4j, suddenly put countless applications at risk globally. It really highlighted how dependent we are on complex chains of open-source dependencies. But there's an interesting and slightly worrying follow-on effect noted in some analyses. When cloud providers like AWS rushed out hot patches for their managed services to mitigate Log4Shell.
Which you'd want them to do, right?
Yeah,
Patch quickly.
of course. But in some cases, the way these patches were applied, sometimes by modifying the runtime environment or injecting libraries, inadvertently caused new problems for some customers. Maybe library conflicts, unexpected behavior, or in a few edge cases, even introduced different potential escape vulnerabilities because the underlying execution environment changed subtly.
Wow, so the fix itself created a new, albeit a different, risk.
In some limited circumstances, yes. It wasn't widespread, but it underscored a crucial point. You can't just blindly trust patches, even from your provider. It reinforces the need for that immutable infrastructure approach. The safest path was often to update the Log4j library in your own application code, rebuild your container image from scratch, thoroughly scan and test it, and then redeploy. Relying solely on platform-level hot patches without revalidating your own app could be risky. Supply chain security isn't just about your direct dependencies. It's about the entire stack, including how security updates are applied.
Understanding these mechanisms is one thing, but seeing how they fail in real-world incidents really drives the point home. Let's dedicate this section to looking at a few high-profile cases that highlight these risks, especially the cost of shared hosts. We have to start with the ECScape vulnerability from 2025. This was specific to ECS on EC2, right?
Yes, ECScape is a perfect and frankly quite scary illustration of what we call a leaky abstraction that can happen because of shared tenancy on EC2. Let's be crystal clear. This attack only works if you have multiple ECS tasks, potentially with different privilege levels, running together on the same underlying EC2 instance. And crucially, the attacker doesn't need to escape their container in the traditional sense, like exploiting Runk. They exploit the trust relationship between the ECS agent and the control plane.
Okay, walk us through the steps. How does an attacker weaponize the orchestration system itself?
Right. Step 1. The attacker gains initial access to a container running within an ECS task on a shared EC2 host. Let's assume this is a low-privilege container, maybe running a web application. Step 2. From inside that compromised container, the attacker queries the instance metadata service, that 169.254.169.254 endpoint again. They steal the temporary AWS credentials associated with the EC2 instance's profile. Now, this is important. This instance profile role is the one the ECS agent software running on the host uses to communicate back to the AWS ECS control plane.
So the attacker now has the identity credentials of the ECS agent for that host.
Exactly. Step 3. Armed with the agent's credentials, the attacker makes calls to an internal, normally legitimate ECS API endpoint, something like Discover Pollen Point. They're effectively impersonating the trusted ECS agent on that host. Step 4 is where it gets really bad. The ECS control plane, thinking it's talking to its legitimate agent, initiates a session or synchronization process. As part of this normal operation, the control plane pushes down configuration information needed by the agent. And disastrously, this information included the clear text IAM credentials for all the other tasks currently running on that same shared EC2 host.
Wait, clear text credentials for potentially high-privileged tasks running right next door, pushed directly to the attacker who is just impersonating the agent.
Precisely. If you had, say, your public-facing web app task running alongside a highly sensitive backend task that had permissions to access critical databases or secrets, the attacker in the web app container could suddenly get the plaintext credentials for that sensitive backend task. Game over.
That is absolutely terrifying. It bypasses container isolation entirely by exploiting the orchestration layer and the shared host identity.
It does. The core lesson from ECScape is brutal. On shared EC2 tenancy, the security boundary between your tasks can be much weaker than you think. It's not just about kernel exploits. The management plane itself can become the attack vector. And what was AWS's primary recommendation for mitigating ECScape? Migrate the workloads to Fargate. Because on Fargate, each task runs in its own isolated micro-VM with its own unique identity credentials. There's no shared host agent identity to steal, and no way for one task's compromise to reveal the credentials of another. The entire attack path is structurally impossible on Fargate.
That makes the argument for Fargate, at least for sensitive workloads, incredibly compelling. It just eliminates this entire class of risk. Let's look at a couple of other incidents that underscore those configuration pitfalls we discussed earlier. Capital One is often cited.
Yes. The Capital One breach is almost the canonical example of least privilege failure leading to massive impact. The initial entry point was actually relatively small, an SSRF server-side request forgery vulnerability in a web application firewall, or WAF, that was misconfigured. That initial foothold wasn't exotic. But the reason it turned into such a catastrophe, the exfiltration of over 100 million customer records, was almost entirely down to the fact that the compromised resource, the WAF or something it could reach, was running with an incredibly overprivileged EC2 IAM role. That role should have had very narrow permissions, probably just enough to interact with specific logging services.
Yeah.
Instead, it had permissions allowing it to list and read data from numerous S3 buckets containing sensitive customer data. The scale of the breach was a direct result of that excessive IAM permission.
So the initial flaw opened a tiny crack, but the overly permissive IAM role blew the door off its hinges and gave access to the crown jewels.
Perfectly put. It wasn't failure of AWS infrastructure. It was a failure to implement the fundamental security principle of least privilege in the IAM policy. And then there's the Scarlet Teal campaign. This one really highlights failures in basic secrets, hygiene, and infrastructure management.
How did that one unfold? Started with a Kubernetes compromise, I recall.
That's right. Attackers compromised a Kubernetes container, likely through a known vulnerability or weak configuration. They moved laterally, but the critical break came when they found something astonishingly careless. They discovered hard-coded, clear text AWS IAM access keys stored inside Terraform state files. And worse, these state files were themselves stored in an S3 bucket that the compromised workload could access.
Oh no, hard-coded admin keys in a config file in S3.
Yes. A fundamental failure of secrets management and IAC, infrastructure as code, hygiene. Terraform state can contain sensitive information, and storing it unencrypted in an accessible location is incredibly dangerous. With those hard-coded keys, which apparently had high privileges, the attackers gained immediate administrative control. They were then able to disable CloudTrail logging to hide their activity, exfiltrate huge amounts of data, over a terabyte mentioned in reports, and even use the compromised account to pivot and attack other related AWS accounts, all stemming from that one basic mistake of leaving secrets lying around in plain text.
Okay, we've seen the architectural risks, the attack vectors like ECScape, and the devastating impact of simple misconfigurations like in Capital One and Scarlet Teal. Let's shift to solutions. How do organizations actually future-proof their container environments? We need to revisit those best practices, maybe with more enforcement in mind. Starting again with IAM because it keeps coming up.
It has to be the top priority. If you do one thing, aggressively enforce the principle of least privilege everywhere. For EKS, leverage IRSA extensively create fine-grained IAM roles, scoped only to the resources each specific service account needs. And critically, don't just rely on developers getting it right manually. You need automated enforcement. Use policy as code tools, things like Open Policy Agent, OPA gatekeepers integrated with your Kubernetes cluster, or AWS config rules, or checks in your CI/CD pipeline. These tools can actually prevent the deployment of resources with overly permissive IAM policies defined in their IAC templates, like Terraform or CloudFormation. Block it before it happens.
So automate the enforcement of least privilege. What about fixing secrets management definitively?
Ban hard coding. Make it a non-negotiable policy. Mandate the use of systems like AWS Secrets Manager or HashiCorp Vault. Configure automatic rotation for secrets wherever possible. Secrets should be injected into containers at runtime, ideally as mounted volumes rather than environment variables, which can sometimes leak into logs. And again, scan your code repositories and configuration files for accidentally committed secrets. Treat secrets like the toxic waste they are if mishandled. This requires a cultural shift for developers, but it's essential.
And for images and immutability.
Embrace GitOps principles. Your infrastructure and application configurations should live in Git. Changes are made via pull requests, reviewed, and automatically applied. Treat your containers like cattle, not pets. If an image needs updating or patching, you don't SSH in. You update the base image or application code in Git, trigger a new build in your CI/CD pipeline, which includes scanning, generate a new immutable image artifact, and redeploy it. The old containers are simply terminated. This avoids configuration drift and ensures consistency.
Right. Rebuild, don't patch in place. Now, runtime defense. Containers are fast, ephemeral. Traditional logging might be too slow. You mentioned eBPF earlier, Extended Berkeley Packet Filter. This seems like a key technology for the future here.
It really is. eBPF represents a significant leap forward for Linux observability and security, and it's particularly well suited for containerized environments. Instead of relying on parsing logs after an event or using slow, higher-level agents, eBPF allows you to run small, safe, sandboxed programs directly inside the Linux kernel itself. These programs can be attached to various kernel events, like system calls, network packet processing, function entries exits.
So if a process inside my container tries to, say, open a sensitive file, like it set a shadow, or make an outbound network connection, an eBPF program hooked into the open or connect system call can see that happening in real time right at the source.
Exactly. It operates at the kernel level, giving it incredibly deep visibility with very low performance overhead compared to older methods. It sees exactly what every process, including those inside containers, is trying to do. Security tools built on eBPF, like the open source project Falco or various commercial offerings, can use this visibility to detect anomalous behavior instantly. For example, why is my nginx web server process suddenly trying to execute shell commands? Or why is this Redis container trying to connect to an external IP address? That's highly suspicious, and eBPF can flag it immediately.
And the really exciting part is that it's moving beyond just detecting things to actively preventing them.
That's the evolution, yes. We're seeing eBPF being used not just for observability, but for real-time enforcement. You can write eBPF programs that don't just detect a malicious system call, but actually block it before the kernel even executes it, or block specific network connections based on behavior. It allows you to build highly customized, kernel-level intrusion prevention systems, IPS, tailored to your application's expected behavior. It's a powerful way to stop attacks, including potential 0 days, much earlier in the kill chain.
Fascinating. Kernel-level visibility and enforcement. Okay, let's bring it all together. We've talked orchestrators, compute options, vulnerabilities like ECScape and runk flaws, configuration failures, and now advanced defenses like eBPF. Revisiting that core architectural choice, EC2 versus Fargate. Given the inherent risks the shared kernel model demonstrated by ECScape, does Fargate effectively become the default recommendation for most security-conscious organizations?
Look, for workloads where you don't need that deep, low-level host access, and where strong security isolation and reduced operational overhead are priorities, Fargate offers a very compelling value proposition from a security standpoint. That micro-VM isolation provided by a firecracker fundamentally eliminates entire categories of risk associated with shared hosts. ECScape becomes impossible, runk escapes are contained, kernel exploits don't cross tenant boundaries, and the burden of host OS patching shifts entirely to AWS. It's a structurally more secure posture for the workloads it supports.
So you're essentially trading some control for a significantly higher baseline of security and lower operational effort.
That's the trade-off, yes. For many modern stateless applications, it's a trade-off that makes a lot of sense. You're investing in built-in isolation rather than constantly working to mitigate the risks of sharing. Of course, if you need that host-level control, you'll stick with EC2, but you absolutely must compensate with rigorous patching, hardening, least privilege IAM, especially IRSA, network segmentation, and runtime monitoring, probably leveraging eBPF.
And this need for a consistent security strategy extends beyond just the main AWS regions, right? What about hybrid or edge scenarios?
Absolutely. The reality for many organizations is hybrid. They might be running EKS anywhere on their own hardware, or ECS, anywhere connecting back to the AWS control plane. The security principles have to remain consistent. You still need robust IAM, you still need container image scanning and SBOMs, you still need secrets management, and you absolutely need runtime visibility and defense, potentially using eBPF-based tools across your entire fleet wherever the containers run. The strategy has to span the entire ecosystem.
This has been an incredibly thorough and, I have to say, slightly alarming deep dive into the world of AWS container security. We've gone from ECS versus EKS through the firecracker isolation model, looked hard at misconfiguration pitfalls, dissected vulnerabilities like ECScape, and explored advanced defenses.
I think the two core truths that emerged are pretty clear, but worth repeating. One, AWS provides an incredibly secure foundation, but ultimately, your configuration choices dictate your actual security posture. And two, your fundamental architectural choice running containers on shared EC2 hosts versus isolated Fargate micro-VMs directly determines your inherent exposure to a whole class of shared host attacks.
So let's leave our listeners with a final thought to mull over. Here it is. If real-world incidents like ECScape demonstrate pretty clearly that the shared host model in EC2, while flexible, is inherently somewhat leaky and forces you into a constant cycle of patching and mitigation work, how much is that low-level control really worth compared to the built-in isolation offered by Fargate? Is the perceived cost-saving or flexibility of EC2 worth accepting that fundamental architectural vulnerability for your sensitive workloads?
That is indeed the critical cost-benefit analysis, the strategic tightrope that modern cloud security teams have to walk every day.
Food for thought. We'll catch you on the next deep dive.